Welcome to this explainer. I am absolutely thrilled to get into today's topic with you, mostly because it completely reshapes how we think about the technology we're using every single day. We often picture artificial intelligence and the cloud as this magical, weightless space, right? Just a purely digital realm where algorithms float around invisibly. But the reality, AI has a massive, very physical footprint grounded right here on Earth. We're talking real steel, real energy, and real water. So today, we're going to make that invisible footprint visible. Okay, let's dive right into this because honestly, this number is just staggering. 6.6 billion. Researchers project that by the year 2027, AI-driven data centers could withdraw up to 6.6 billion cubic meters of fresh water. Now, to put that into perspective, that is more than 4 times the annual freshwater usage of the entire country of Denmark. We are talking about a scale of resource consumption that's historically unprecedented for a digital technology. Real quick, here is our roadmap for the explainer. We'll uncover the hidden costs of AI, compare them to our daily digital habits, and look closely at local water conflicts. Then, we'll rate AI efficiency, explore some really cool data center innovations, and map out what a sustainable AI future actually looks like. All right, Section 1, the hidden cost of AI. When we talk about AI's growth, energy demand is literally skyrocketing. We're looking at estimates suggesting AI alone could account for over 650 terawatt-hours globally by 2030. But you might be wondering, how much are you personally contributing to that? Well, individually, it's actually tiny. An average ChatGPT query uses less than 1/15 of a teaspoon of water. If you compare that to producing a single pair of jeans, which takes roughly 7,500 liters, a few prompts seem completely harmless. The true impact is only revealed when we zoom out to a global scale. Section 2, AI versus daily digital habits. To really contextualize these massive numbers, let's compare it to stuff we already do. 10 standard AI queries use about 4 watt-hours of energy. That's actually way less than streaming 10 minutes of Netflix, which uses 12.8 watt-hours, or scrolling TikTok, which uses a whopping 66 watt-hours. I guess it's proof that doom scrolling is heavy in more ways than one, right? So on a per-interaction basis, standard AI is quite light. But remember, we are talking about billions of simultaneous queries, drastically reshaping our baseline infrastructure. Furthermore, the specific type of AI you use matters immensely. A standard query uses just about 0.34 to 0.42 watt-hours in a few milliliters of water, which is incredibly close to a standard Google search. However, these new, highly complex reasoning models, like OpenAI's LL3 or DeepSeek's R1, they change the game entirely. Because these models engage in extended chain of thought processing, they can consume 10 to 70 times more energy and water per prompt. When you multiply that by billions of daily requests, you can see why scale becomes the core issue. Section 3, the local water conflict. So while the cloud operates globally, its physical infrastructure sits right in our backyards. According to the UK government's Digital Sustainability Alliance, global demand for freshwater is expected to exceed supply by 40% by the end of the decade. Critically, 55% of global data centers are located in river basins with a high risk of water pollution. On top of that, nearly 68% of data centers are near protected or key biodiversity areas. This creates a very real tension between our rapid technological expansion and vulnerable local environments. To see what this actually looks like on the ground, consider the city of West Des Moines, Iowa. During the peak heat of summer, a single Microsoft data center campus there draws about 43 million liters of water a month just to cool its servers. That single facility accounts for roughly 6% of the entire city's total water usage. And because water is such a localized and highly seasonal resource, this puts immense pressure on public utilities and local populations in drought-prone or stressed areas. In the UK, for instance, Thames Water has previously warned that data centers could face restrictions on their water use during the hottest, driest times of the year. Public water systems are simply struggling to support the peak summer demands of these massive facilities without risking the supply for local residents. Section 4, rating AI model efficiency. Now, what's really interesting here is how we might fix this, and the answer lies in the massive efficiency gaps between the models themselves. An academic benchmark testing 30 models revealed a 200 times difference between the most and least efficient options. You'll notice how Meta's Llama and Google's Gemini use fractions of a watt-hour and barely a drop of water, while a heavy reasoning model like DeepSeek R1 uses nearly 24 watt-hours and significantly more water for a similar short query. That is a massive leap that directly multiplies grid and local resource consumption. What you should really take away from this is that the environmental footprint of a prompt is no longer just a fixed cost. It's actually a design choice. It's deeply tied to the model architecture and the specific energy grid it runs on. This means businesses and developers can instantly and drastically reduce their footprint just by making strategic choices about which AI model they deploy for specific tasks. A fantastic concrete example of this is from Davira, a company that runs lifecycle assessments. By using highly efficient AI models like Claude Sonnet to automate data extraction, they completely avoid the hours of manual consulting, commuting, and office energy usually required. The result? Their well-designed AI process actually reduces the environmental footprint of an assessment by 50 times compared to traditional manual methods. So AI can absolutely be a tool for sustainability if we use it smartly. Section 5. Innovations in Data Centers. Of course, the tech industry isn't just sitting by. One of the biggest shifts happening right now is in how these facilities are kept cool. Traditional evaporative cooling relies on evaporating millions of liters of fresh water just to stop the servers from melting down. But today, we're seeing some brilliant modern innovations. Google, for example, utilizes air cooling at their site in Waltham Cross to drastically limit water usage. And Microsoft is deploying closed-loop cooling systems that recirculate fluid without evaporation, which saves over 125 million liters of fresh water per data center every single year. In fact, all 4 major hyperscalers are deploying some incredible sustainability targets. Microsoft is aiming to be carbon negative by 2030, heavily investing in waterless cooling. Google is pioneering 24/7 carbon-free energy and has committed to replenishing 120% of the water it consumes. AWS is targeting being water positive by 2030 and is even investing in modular nuclear reactors. And Meta? They've been running on 100% renewable energy since 2020, achieving some of the absolute best operational efficiency scores in the industry. Finally, Section 6, a sustainable AI future. Let's move ahead and see how this builds a vision for the future. How do we ensure these data centers operate in harmony with our ecosystems? Looking at the industry roadmap, we see some clear momentum. Microsoft reaches its 100% renewable electricity target in 2025. And while AI water withdrawal risks might peak around 2027, by 2030, we're seeing massive commitments to net zero and water-positive operations, pushing all the way to AWS's net zero target in 2040. The industry is steering heavily towards zero water cooling and carbon-free energy. Ultimately, the crucial takeaway here is that balancing AI's incredible world-changing capabilities with its immense physical demands requires strict discipline. If AI is going to be the new electricity of our era, it has to be measured, monitored, and entirely decarbonized right at the source. It requires deeper transparency, much smarter workload designs, and above all, profound respect for local ecosystems and water supplies. Which leaves us with this final thought. Every time we type into a chat box, we are literally pulling resources from the physical world. So what is the invisible environmental cost of your next AI prompt? And knowing what you know now, what model will you choose to answer it? Thank you so much for joining me on this explainer, and I hope this gives you a powerful new perspective on your digital footprint.